Hello everyone, I am Dimpy Kalita and along with my group partner Daisy Bordoloi presenting a brief overview on our final year project that is done under the supervision of Dr. Anjan Kumar Talukdar and Professor Kandropa Kumar Sharma and co-supervision Dr. Surajit Deka. The topic of our project is vision-based people counting system in indoor and outdoor environment using deep learning models. So let's get started. These are the outlines of our project. Let's start with the introduction. People counter mainly aims at automatically estimating the number of people in places. Earlier, these counting systems were done manually or based on infrared sensor, but nowadays computer vision based methods are more reliable. Motivation. There are innumerable counter systems, but the society wants all in one solution. Thus, we took the initiative to propose a system that solves a major problem. Objective. Our main objective is to build a people counter system using computer vision and to help future systems requiring people counting as a feature in their system. These are some of the literature review that we have taken as references. Problem formulation. The main challenges that we have got are occlusion, cluttered background and illumination. These are the tools that we have taken or used for our project. This is just a basic block diagram of detection that we have considered. Phase 1 Detection of model using a one-stage algorithm, that is single shot detector SSD. Object detection. It is basically a technique for locating objects in an image and video. They are widely used in computer vision tasks such as face recognition, self-driving car, and many more. There are various algorithms of object detection: Viola Jane's histogram of oriented feature, single shot detector, you only look once, faster reason-based convolutional neural network. For in our project we have used SSD, YOLO, faster RCNN. Single shot detector. It is a deep learning algorithm that is used for object detection. It consists of two main components: backbone model and SSD model. This is the SSD architecture with mobile net. An input image is taken and is sent to a mobile net for extracting features. These are six convolutional layers which will perform classification object detection tasks. SSD make many predictions, so non-maximum suppression is used to remove the duplicate predictions. When the overlapping of this boundary box and ground truth boxes is greater than 50%, then we'll pick those boxes. Centroid tracker algorithm. It is a technique that is used to identify the object. It mainly consists of 5 steps. After detection of the person, we need to track them. We will assign a new ID to every detected person, draw a box over the person and measure the centroid. For example, two persons are detected here and in the next frame, both the persons move to a different location by yellow color. Also, there is a new person detects here. Now the method to identify that these two are same person from previous frame is we calculate Euclidean distance from every old centroid to every new centroid. The closest pair will be considered as the same person. So in the final part we can see same ID is given to first two person and a new ID is given to third person. Now we cannot find the ID for a consecutive frame, then we will deregister the ID from our array. Block diagram of working model. It mainly comprises of two phases. Setup phase. The mobile net model is trained with dataset. Whenever any object comes in front of camera range, it creates a class for each object and class moves to the detection phase. During detection phase, the mobile net SSD detects an object in front of boundary box and extracts an object's feature, and centroid tracker tracks the person and assigns a unique ID to each person. If the detected person is real, then the model makes prediction. These are some of the results that we have got. Phase 2 Comparison between faster RCNN and YOLO. People counting using YOLO model. Faster RCNN, it is an object detection architecture that uses convolutional neural network. It is a two-stage algorithm. These are the results of faster RCNN. Next is YOLO. YOLO is a machine learning algorithm that uses features learned by a deep learning neural network to detect an object. These are the results. Comparison between faster RCNN and YOLO. After comparing the two models, we found YOLO is faster than RCNN. Also, accuracy of YOLO V3 is 92% and that of faster RCNN is 90%. These are the graph. As you can see, process of YOLO. First we have to set a camera correctly. After that, the next step is setting the detection threshold. The detection results below the threshold, then it will not be counted. The next step is we detect people through retraining a CNN. YOLO divides the image into grid cell, and for each grid cell it predicts two object boundary box as well as confidence score for those boxes. The next step is consists of detecting and counting people based on appropriate boundary selection. It chooses different boundary according to the actual situation. The next is counting information of the previous step is now processed in the fourth step. In a selected boundary area, the boxes number accumulates and constantly updates. In the fifth step, we output real-time people counting information. It will directly show real-time people counting information in video images. This is the block diagram of counting phase. Implement of this model is similar to CNN. For feature extraction, the initial convolutional layers of model is used, whereas the other connected layers helps on prediction of the output probabilities and coordinate of boundary box. It divides the input into grid cell and then the object is detected. If the object falls into grid cell, then for its grid cell, the model further predicts detected boundary box and confidence map value. The confidence map shows the score of each detected object along with detected boundary box. Once the boundary box is detected, the next step is to predict the class of object as person or no person. The class is assigned to each boundary box as a person or no person. After person detection, people counting is performed. For counting, the classification box information is used. The counter is set for each frame image which convert the respective person boundary box by assigning count number. This is the result of YOLO V5, YOLO V8, and this is the statistical results that we have got. This is the YOLO V4, result of YOLO V4. So now the limitations, the drawbacks that we have got of all the models is that overlapping and densely packed individuals might be detected as a single object, leading to inaccurate counts. The model will not generalize well to entirely different scenarios. Future direction. The algorithm detects the person whose full body is included in the frame, which regress the accuracy in crowded scenes, which could be improved in future by expanding the model to train to detect people using only the heads. It can also extend to find a person's position in a scene, recognize gender, and estimate age. So of all the three models that we have used, we have got that YOLO has the higher accuracy, and we have also implement a real-time people counting using YOLO V4, we got the accuracy 80%. Now let's start with the demo video.
First, we explored a one-stage object detection algorithm named Single Shot Detector (SSD). After testing with various samples, we found that when a people get collided or occluded, it cannot detect the other person. So we moved forward with a two-stage object detection algorithm named Faster RCNN. After exploring faster RCNN, we did not get the accurate result. The accuracy is 90%. As you can see in the result that the people standing at the back are not detected. Next, we explored various versions of YOLO. The working of YOLO is same as the SSD, as both of them are one-stage detector. First we tried YOLO V3. The results are better than the previous models. As you can see that the model is predicting every object present in the image, but only the persons are counted. Next is YOLO V5. Here also we got better result than the previous models. Here we label the class and score. Next we explored YOLO V8. Here we tried different video samples. Each frame is predicting the object and frame per second is fast here. So the result that we have got are accurate. It's approx 90% accurate. Lastly, we have tried YOLO V4 for real time. First, we have tested an image and then on webcam images. We created our live video stream using our webcam as input. The video stream frames are fed as input to YOLO V4. YOLO V4 gave the accuracy is about 80% and F1 score is 0.8.